In this video, we want to start talking about what's known as a limit. So limits are kind of the foundation of calculus. So this is where we start getting on the border of pre-calculus and calculus material. So this will kind of set the foundation for everything we're going to talk about in calculus. So first, I just want to kind of talk about the idea of what a limit is, just verbally, before we start to, write down everything mathematically. And actually, let's go ahead and look at some graphical examples of this as well. So here I have this graph. So what this graph is a graph of the line x plus 3. That is y equals x plus 3, but not just that line. It's actually y equals x plus 3 when x doesn't equal 3. And y equals 4 when x does equal 3, or I'm sorry, 7. Right, so we have this point at 3, 7. So you can see that there's a hole in the graph right here at 3, 6. So when x equals 3, and I'll go ahead and write, let me just write out what this equation is mathematically here. So we kind of have that for reference. So if we think of it as a function, we're thinking of this as a piecewise function where f of x equals x plus 3 if x doesn't equal 3, and 7 if x does equal 3. Okay, so this is the function that we have graphed right here. So the idea of a limit. Okay, so a limit is going to ask the question, okay, if we want to know the limit of a function as x approaches 3, what we're asking is, okay, forget about the actual value at x equals 3, right? The actual value at x equals 3 is 7, right? F of 3 equals 7. So we want to ask a different question, and it's going to be known as the limit. So we want to know, what is the limit as x approaches 3 of f of x? And in some cases, this will be the same thing as the output. But in cases like this, it's not going to be, because it's going to say, okay, ignore what the actual output is. What does the function look like it's getting close to? Okay, and we can see here, okay, it looks like it's, and you can see it says it's undefined right here, right? When we get to 6. But the function looks like it's approaching 6, right? As x gets closer to 3. Let me show the x-axis on here. Right, so as x approaches 3, it looks like f of x is approaching 6. So the actual output is at 7, but we want to ignore the output when we're talking about limits. We want to know, what does the function look like it's getting close to? And what exactly do we mean by looks like, right? How do we say that mathematically? So what we really mean is, if we were to take any point that's really close to this, and we kind of look for a pattern of where the y values are getting close to. So like 2.996, it's 5.996. 2.999, the output is 5.999. And on the other side, we have 3.003 is 6.003. 3.006 is 6.006. So by all accounts, it looks like this function is getting close to the point 3, 6. So it's kind of like, if we didn't know any better, if we didn't know what the output actually is, which is 3, 7, what would we assume that it is? Okay, so that's one way to think about it. So that's kind of the informal idea of a limit. Another thing about this concept of a limit is it basically is looking at, okay, if we get infinitely close to something, then what point are we at? So on that example here, if we get infinitely close to this point right here, sorry, I'm clicking on the wrong thing here. If we get infinitely close to this point, then what is the output that we are approaching, right? And this idea, the same kind of idea has been used in a lot of mathematics all the way back to the ancient Greek times, right? Way before the invention of calculus. Calculus wasn't around until the 1600s with Newton inventing it or discovering it, or however you want to say it, for physics, right? But all before that, all the way back in the ancient Greek times, Archimedes was trying to figure out the area of a circle, right? Simple thing for us to do nowadays, but back then when you're just working with like a ruler or a protractor, like those kind of basic tools, it's hard to find the area of a circle because, of course, as you know, we kind of talked about in the unit circle video, right? This comes out to pi r squared. I guess we only talked about the circumference, but the area also has pi in it, right? So pi is not an easy thing to measure. So it's hard to find the area of a circle. So what he did was he considered, basically he considered a square, then he considered a pentagon, right? And then he kept increasing the sides. So he would then look at a 6-sided polygon, a 12-sided polygon, a 30-sided polygon, etc. And he would just look for the pattern and see that, okay, eventually if we were to look at a polygon with infinite number of sides, that's going to be indistinguishable from a circle, right? Those, if you just keep adding more sides to it, it gets more and more rounded. And we can find the area of a polygon with, 100 sides or whatever. So we can kind of see where this pattern is going. And that led him to the area of a circle. It was known as the method of exhaustion back then. So this idea has been around for a long time. And, basically Newton and also Leibniz came around and applied this idea to functions. And that's how we ended up with calculus. Okay. Obviously, huge oversimplification of the whole ordeal. That's about 2,000 plus years of mathematics there. So let's go ahead and start formalizing this idea of what exactly do we mean by a limit mathematically. So let's just write out the formal definition of this first. Okay. So we're going to say, let f of x be a function defined at all values in an open interval containing a. Okay. So a here is going to be the number that we're approaching. So that would have been 3 in the last example. So first of all, what we're saying so far is that around the number that we're looking at approaching, the function needs to be defined in an open interval around a. So that means like if a is 3, then it needs to be defined in, say, 2, 3, the interval, or sorry, 2, 4, an interval containing 3. With the possible exception of a itself. Okay, so it doesn't need to be defined at a. In the last example, it was defined at a, but it was defined at a different point, but it didn't need to be defined at a at all. So, all right, so then we'd say if all values of the function f of x approach the real number L, so this is what we call the value of the limit here, as the values of x approach, A, just putting A in quotes here to kind of distinguish it. Then we say the limit of f of x as x approaches A is L. Okay. So mathematically, we write it as we did up above, but now we'll write it with some general letters. Right? So we have the limit of f of x as x approaches A is equal to L. Okay. So to kind of sum this up, a shorter way of saying all this is that as x gets closer to A, f of x gets closer to L. And when we can make this very precise, it's a little trickier to kind of work with the more precise definition of a limit. So we'll look at that a little bit later. I think it's better to kind of get an intuition of it first, because the more precise limit, it can be kind of intimidating and tricky. But basically the idea is that if x and A get arbitrarily close, then f of x and L should also get arbitrarily close. So if you can get, if in this example up here, as x gets closer and closer to 3, f of x should get closer and closer to 6, right? Because that's what the actual limit was. So even though the output was 7, the limit here is 6. So we could get x and 3 get arbitrarily close together, and that will imply that f of x and 6 are arbitrarily close together. So let's look at a couple more graphs here so we can kind of demonstrate this idea. So let me, we'll clear this graph out here, and we'll look at a good example of this is a rational function. X squared minus 4 divided by x minus 2. Okay. So why this function? First of all, actually, let's go back and look at mathematically what this function is. Okay, we have x squared minus 4 over x minus 2. If we factor the top here, we have x plus 2, x minus 2 over x minus 2. So these cancel. So this is equal to x plus 2. But are these the same, right? If we think about them in terms of functions. If we have the function f of x equals x squared minus 4 over x minus 2, and g of x equals x plus 2, is f of x equal to g of x? Okay, and the answer is no. And why not? Well, if we're thinking about them in terms of a function now, we have to consider their domain. And 2 is in the domain of g, but 2 is not in the domain of f, right? So they're equal everywhere except for at one point, namely x equals 2. F of x is undefined at x equals 2. G of x is 4 at x equals 2. So they're not quite the same. So if we're looking at this function on the left here, the f of x, if we go back on the graph here, what happens at x equals 2? Okay, so we said that's that would be f of x equals 4 on G. If we hover over this point here, it's a little hard to get precise, but we can see it's undefined. Okay, and on this graphing calculator, it's very hard to see. This is normally where we would put an open circle. So one way we can kind of put that in manually, just to make it a little easier to see, is we could just put in that point, and maybe we can, if you hold this, you can change the color and you can change it to an open circle or whatever you want to do. So we'll put an open circle right there just so it's easier to see for us. That's what I was doing on the last one as well. So anyway, so we can see that this function is undefined at 2. So in other words, f of 2 is undefined. But we can talk about the limit of f of x as x approaches 2. And we can see that as x is getting closer and closer to 2, f of x is getting closer and closer to 4. Okay, so we would say that the limit as x approaches 2 is equal to 4 in this case. So even though the function is not defined at 4, we can still define the limit of this function at x equals 2. Right. Now I've tried to make a point that we need to look at where the function is approaching on both sides here, right? So we look at both sides of the x's. So as x is coming into 2 from the left side and from the right side, they should be going to the same place. So if they're not, that'll cause issues. And we'll look at all these different cases separately as we keep looking at these functions. But let me just show an example of what that kind of thing would look like. So if we consider the absolute value of x minus 2 divided by, I think I've messed up a little here. The absolute value of x minus 2 divided by x minus 2. Okay. Let's see what this function looks like. So this is a weird looking function. And again, if we go back, let's just look mathematically at what this function would look like. Okay. X minus 2 divided by x minus 2. Well, if you remember, for the absolute values, we can break this up into a piecewise function that changes depending on if x is greater than 2 or less than 2. So if x is greater than 2, this is going to be x minus 2 over x minus 2. If x is greater than 2. And if it's less than 2, it's going to be negative x minus 2 over x minus 2. And this equals 1, and this equals negative 1. Right? So this is reflected on the graph here. Okay, so if you can see here that the function's equal to 1 if x is greater than 2, and negative 1 if the function is if x is less than 2. And you can see that at 2 it's undefined on both sides. So what would we say the limit as x approaches 2 is in this case? Well, here it's a little bit harder to reconcile because f of x is approaching negative 1 when we're coming in from the left side, right? I mean, in fact, it is negative 1 for all of these points. So when we get to 2, we don't expect it to be any different. And then it jumps up over here, though. And if we look at x approaching 2 from the right side, it looks like it's approaching 1. So there's this conflict here, where from the left side, it looks like it's approaching negative 1. From the right side, it looks like it's approaching 1. So in this case, we say that the limit does not exist. Okay, if there's no clear point that the function is approaching, then we don't have a limit. Okay, so just like for a function, we don't have to have an output. We can have an undefined output. Same idea with a limit. We say the limit does not exist if there's no clear point that it is working towards. Okay, last case I want to look at for this video. let's look at the rational function 1 over x minus 2 squared. Okay. Now this is an interesting case where if we look at, again, the limit as x approaches 2, okay? 2 specifically because that's where the function is not defined, right? So we know that the function kind of blows up at this point. If we keep plugging in values closer and closer to 2, the values just keep getting larger and larger and larger. And we said that this means that we have a vertical asymptote here. And namely, like this function, it kind of looks like it's hard for us to see because it's so large, but it does kind of look like they're both going to the same place, right? But because they're just blowing up completely, we still say in this case that it's not approaching a number. In fact, what we say is that it's approaching infinity. So sometimes we might write that the limit as x approaches 2 is equal to infinity, but that's really another case of the limit not existing. Most of the time we define a limit to be, as we did in our definition here, right? We defined it to be approaching a real number L. Infinity is not a real number, right? It's a concept, it's not a number. So in this kind of definition, we still say that the limit does not exist. But we also might write that the limit equals infinity because it still could be helpful information. So equaling infinity means it doesn't exist. But we could write it either way. So what I mean by that, I can actually write it out here. So the limit as x approaches 2 of, what was the function? 1 over x minus 2 squared equals, you could say equals infinity, or you could say DNE, which means does not exist. Okay. So equaling infinity means it doesn't exist, but sometimes we make the choice to write it this way because that's still helpful information.